Have you ever wondered how chemists can look at a molecule and instantly know where its bonds are, which atoms are connected, and even predict its shape? Take water, carbon dioxide, or ammonia. They all behave differently. But how can we see what's happening inside molecules when atoms are far too small to observe directly? The answer is a simple, but incredibly powerful tool called the Lewis structure. In today's video, you're going to learn to draw one yourself, from scratch, for any molecule you encounter. Welcome back to our chemical bonding series. In Episode 1, we explored why atoms bond at all. Episode 2 was ionic bonding, atoms giving and taking electrons to form charged ions. Episode 3 was covalent bonding, atoms sharing electrons to fill their outer shells. And Episode 4 was the metallic bond, the sea of delocalized electrons that makes metals bend, shine, and conduct electricity. Today, Episode 5, we bring it all together. Because once you know that atoms share electrons in covalent bonds, the very next question is, how do we show that sharing visually? How do we draw it? The answer is the Lewis structure, and it was invented by an American chemist named Gilbert N. Lewis back in 1916. A Lewis structure, also called a Lewis dot diagram or electron dot structure, is a two-dimensional drawing that shows how atoms in a molecule are connected and how their electrons are arranged around them. A Lewis structure is a diagram that shows which atoms are connected, how many bonds exist between them, which electrons are shared, which electrons remain unshared. Instead of drawing every electron in an atom, Lewis focused on the most important ones, the valence electrons. Remember from our previous videos, in most Lewis structures, every atom wants to be surrounded by 8 electrons. 4 pairs. This is called the octet rule. Think of it like a seating arrangement at a dinner table. Every atom wants 8 electrons around it. It doesn't matter whether those electrons are shared with a neighbor or sitting alone. 8 is the magic number. And Lewis structures show us exactly how that arrangement is achieved. All right, let's build a Lewis structure step by step. No matter how complicated a molecule looks, we can usually draw its Lewis structure using 4 simple steps. Step 1. Count total valence electrons. Step 2. Determine the central atom. Step 3. Connect atoms using single bonds. Step 4. Distribute remaining electrons to satisfy octets. Let's see how this works in practice. We'll use water, H2O, as our first example, then move to something more complex. First, count valence electrons. Oxygen has 6. Each hydrogen contributes 1. Total, 6 plus 1 plus 1 equals 8 valence electrons. Next, choose the central atom. Hydrogen can form only one bond, so oxygen goes in the center. Now connect the atoms. H-O-H. Each single bond uses 2 electrons. 2 bonds use 4 electrons. We started with 8 electrons, so 4 remain. We place them on the oxygen as 2 lone pairs. Why oxygen and not hydrogen? Because hydrogen only needs 2 electrons to be satisfied. It's the only element with a duet rule instead of an octet rule. Its shell is full with just 2 electrons. Now oxygen has 8 electrons around it. Each hydrogen has 2 electrons. Everyone is stable. This is the Lewis structure of water. Simple and elegant. Let's try a slightly bigger molecule. Carbon dioxide, CO2. Carbon contributes 4 valence electrons. Each oxygen contributes 6. Total, 4 plus 6 plus 6 equals 16 valence electrons. Carbon is least electronegative here, so it goes in the center, with 1 oxygen on each side. 3 atoms, 2 single bonds to start. These 2 single bonds use 4 electrons. 12 electrons remain. Take your remaining electrons and distribute them as lone pairs, starting with the outer atoms first. Place electrons around the oxygen atoms first. After doing this, both oxygens have octets. but carbon only has 4 electrons around it. Carbon is not stable yet. What do we do? If any atom, especially the central atom, doesn't have a complete octet, form multiple bonds by converting lone pairs into bonding pairs. In CO2, carbon needs 4 more electrons. Each oxygen has lone pairs to spare, so we take 1 lone pair from each oxygen and convert them into a second bond with carbon. Those single bonds become double bonds. This is the key insight of Step 4. You don't add new electrons, you just rearrange existing ones. Take a lone pair from a neighbor, make it a shared pair instead. The total electron count stays the same, but now everyone is happy. A double bond, shown as 2 parallel lines, counts as 4 electrons. A triple bond, shown as 3 lines, is 6. Some molecules, like N2, nitrogen gas, have a triple bond. Ake nitrogen has 5 valence electrons. Total equals 10. After the triple bond, 6 electrons, each nitrogen gets 1 lone pair, 2 electrons. Both octets satisfied. Total used, 10. Perfect. That's 3 shared pairs holding those 2 nitrogen atoms together incredibly tightly, which is why nitrogen gas is so stable and why it makes up 78% of our atmosphere. Next step is where things get really interesting, and where students often get tripped up. We need to check formal charges. A formal charge is a way of checking whether our Lewis structure is the best possible arrangement of electrons or not. It's not a real charge. It's a bookkeeping tool. The formula is simple. Formal charge equals valence electrons minus lone pair electrons minus half of bonding electrons. The best Lewis structure is the one where formal charge is closest to 0, and where any charges that do exist match the actual charge of the molecule or ion. Let's try it with CO2. Carbon has a double bond to each oxygen. Carbon's formal charge: 4 valence electrons minus 0 lone pair electrons minus half of 8 bonding electrons equals 4 minus 0 minus 4 equals 0. Perfect. Each oxygen, 6 minus 4 minus half of 4 equals 6 minus 4 minus 2 equals 0. All formal charges are 0. This is a great Lewis structure. Now imagine we had drawn CO2 with a single bond on one side and a triple bond on the other. Let's check. The triply bonded oxygen would get a formal charge of -1, and carbon would get +1. That structure is still valid, but it's less ideal because charges are not 0. The double-double bond structure wins. Golden rule applicable here is that the Lewis structure with all formal charges equal to 0, or the smallest possible charges, is always preferred. But chemistry has one more trick up its sleeve. Not every atom follows the octet rule. There are 2 important exceptions you need to know. Exception 1. Expanded octates. Elements in period 3 and beyond, like phosphorus, sulfur, and chlorine, can have more than 8 electrons around them. This is because they have d orbitals available, which gives them extra space for electrons. Phosphorus pentachloride, PCl5, has phosphorus at the center bonded to 5 chlorine atoms. That's 10 electrons around phosphorus. Sulfur hexafluoride, SF6, has 12. Sulfur is at the center with 6 single bonds to fluorine, 12 electrons around sulfur. Each fluorine still has its octet. Formal charges all 0. Valid. These are called expanded octets, and they're completely valid for period 3 and higher elements. On the other end, some atoms are perfectly happy with fewer than 8 electrons. Boron is the classic example. In boron trifluoride, BF3, boron only has 6 electrons around it, 3 single bonds, no lone pairs. It's electron deficient. Beryllium can be even more extreme. In BeCl2, beryllium only has 4. These molecules are electron hungry. They behave as Lewis acids. They will readily accept lone pairs from other molecules. This is why BF3 is used as a catalyst in many industrial chemical reactions. Its incomplete octet makes it reactive. Remember, hydrogen, duet, boron, sextet, and third-period elements, expanded octet, are the three big exceptions to the octet rule. You might be wondering, is this just a classroom exercise? Why do chemists still use Lewis structures today when we have quantum computers and molecular simulation software? Because Lewis structures are fast, visual, and remarkably accurate. They're the first step in predicting molecular geometry using VSEPR theory, which tells us whether a molecule is linear, bent, tetrahedral, or trigonal planar. Shape determines everything: polarity, reactivity, biological activity. Drug design. Before synthesizing any new drug, chemists draw Lewis structures to predict how a molecule will interact with proteins in the body. The position of lone pairs tells them where hydrogen bonds will form. That's how medicines are designed at the molecular level. Lewis structures of ozone, O3, and nitrogen dioxide, NO2, explain how these molecules react with sunlight to create smog, or how ozone is destroyed in the stratosphere. The structure predicts the reactivity. Why does carbon dioxide dissolve in water to make carbonic acid? The Lewis structure of CO2 shows lone pairs on oxygen, electron-rich sites ready to grab a proton. That's the chemistry behind every fizzy drink on the planet. Lewis structures of silicate minerals explain the properties of glass, ceramics, and even the rocks beneath our feet. The A-silicon-oxygen tetrahedron, a central silicon bonded to 4 oxygens, is the building block of Earth's crust. One simple drawing, infinite applications. That is the power of the Lewis structure. In Episode 6, we will take Lewis structures one step further. We use them to predict the actual 3D shape of molecules using something called VSEPR theory, valence shell electron pair repulsion. Once you know the Lewis structure, you can predict whether a molecule is bent like water, flat like CO2, or pyramidal like ammonia. Hit like if this helped, subscribe so you don't miss Episode 6, and drop your Lewis structure questions in the comments. I read every single one.